Assalamu alaikum. My name is Rabia-431014123-summary, and today I will be summarizing section 2.4 to 2.9 of our text. These sections cover the powerful techniques we use to model different physical systems. Uh, this powerful These sections cover the powerful techniques we use to model different physical systems, from electrical circuits to mechanical gears, using transfer functions. Let's begin with section 2.4, electrical network transfer functions. The primary goal here is to create mathematical models of electrical circuits that relate the output signal to the input signal. We do this using Laplace transforms. The core of these methods is treating the fundamental circuit components in terms of their frequency domain impedance. As you can see, a resistor impedance is simply its resistance R, and inductor's impedance is Ls. Also, the capacitor's impedance is 1 over Cs. By using these impedance values, we can apply standard circuit analysis techniques to derive the overall transfer functions of a network. Several methods can be used to find transfer functions. Mesh analysis uses Kirchhoff's voltage law, allowing us to sum the voltages around an enclosed loop in a circuit. The governing equation is that the sum of impedances multiplied by the loop current equals the sum of the applied voltages. And for the nodal analysis is based on Kirchhoff's current law, summing the currents at a specific nodes. This method often uses admittance, which is simply the reciprocal of impedance. And for simpler series circuits, voltage division provides a very quick way to find output voltage. The formula shows the output voltage is the input voltage times the ratio of the output of the output impedance of the total series impedance. On ohms are active electronics component. This section also covers active components like operational amplifiers or OMB-AMs. The example here shows an inverting OB-AM where the output is scaled and inverted version of the output. The transfer functions for this configuration is elegantly simple. It's the negative ratio of the feedback impedance Z2 to the input impedance Z1. This specific circuit is an example of PID controller, a crucial component in many control systems. As we see here, we use Z1 equal 1 over Cs plus 1 over R, which is the summation to sum the circuit, and then Z2 equal R2 plus 1 over Cs2, which is in series. So the final is V output over V input. Now let's shift from the electrical domain to the mechanical section. 2.5 covers translation mechanical systems, which are systems that move in straight line. Just like with circuits, we can define the impedance of the core components. A mass is the energy storage element with an impedance of ms square, like what we see here. Oh, sorry, this is ms square. A spring also stores energy and has an impedance of K. A viscous damper dissipates energy with an impedance of Vf square. of Pf per second. The governing law for these systems is Newton's second law, where we sum all forces acting on a body to zero. To find transfer function, we draw free body diagrams for each mass, write the equations of motion, and then solve those simultaneous equations. Find the transfer function for the systems with two masses. As we said, identify the degree of freedom, then which determines the number of equations needed. Draw free body diagram for each mass. Use superposition to find all forces acting on each mass. Write the two simultaneous equations of motion using Newton's law. Solve the system of equations to find the desired transfer function. Like this, we have transfer functions, one equation of motion. This is for the mass. The mass has k, which is the spring in the left side, and we have the displacement xt and the forces ft in the right side. Also, we have the viscous in the left side, also which have the mass in the left side. Which is the equation is m d square x over d of dt square plus phi f dx over dt plus kx equal ft. This is the simple equation of the simple system. So after that, we take the Laplace for this equation. So it will be ms square x s plus f phi f, which is here is s, plus kx equal fs. After simplify, this will be the final equation. Uh, and Section 2.6 introduces rotational mechanical systems, which are the direct analog of the translational systems we just discussed. The principles are the same, but the variables change. Force becomes torque. Linear displacement becomes angular displacement, and mass becomes moment of inertia. The component impedances are defined in the same way, using gs squared for inertia, k for torsional spring, and ds for rotational damper. Building on this, section 0.27 adds gears into our systems. Gears are used to gain mechanical advantage, essentially trading speed for torque. For lossless gears, the angular displacement ratio is inversely proportional to the number of teeth on the gears, while the torque ratio is directly proportional. A key technique for simplifying systems with gears is reflecting impedances from one shaft to another. By reflecting all the load impedances back to the motor shaft, we can analyze the entire system with a single equation of motion. The rule is that an impedance is reflected to a destination shaft by multiplying it by the square of the gear ratio, which is the number of teeth on the destination gear divided by the number of teeth on the source gear. Mechanical words. To simplify analysis, we can reflect all mechanical impedances from the load side to the motor side. A rotational impedance is reflected from a source shaft to destination shaft by multiplying by the square of the gear ratio, as we say. This is example, which is giving this equation, which is moment of inertia is square plus the damper, rotational damper s plus k multiplied by the angular displacement equal torque s n2 over n1, which is torque reflected by n2 n1. Okay, g which is moment of inertia equal moment of inertia 1 into over n1 square plus moment of inertia 2. This is 1, this is 2. Damper equal damper 1 into over n1 square plus d2, which is d1, d2 here. Okay. Gs equal angular displacement over torque equal n2 over n1 moment of inertia is square plus torsional damper plus k. Section 2.8 brings the electrical and mechanical worlds together in electromechanical systems. Using the armature-controlled DC motor as the prime example, these systems are designed to convert electrical voltage into mechanical motion. Two key principles are at play. Back EMF. The motor generates its own voltage called back electromotive force, which is proportional to its rotational speed. Motor torque. The torque produced by the motor is proportional to the armature current flowing through it. By writing equations for both the electrical circuit and the mechanical rotation and then combining them, we can derive the complete transfer function relating to the input voltage to the angular position of the motor shaft. As noted, this requires us to use the total inertia and damping at the armature, including any reflected loads from gear. These are our examples: DC motor and load, which is given the system and torque speed curve figure, and find the transfer function, angular over E. Okay, moment of inertia M equal moment of inertia A plus moment of inertia L multiplied by N over N square equal, which is 5. This from figure 2.39. This is L and moment of inertia A here. I can add them here, and you have torsional damper or total damping dm equal dA equal 2 plus dl, which is here, and n1 over n2. This is n1, this is n2. After that, we wrote the equation k over ra equal t stall over ea equal 5. Then we have key b. Then we will substitute in this equation. Finally, section 2.9 discusses the fascinating concept of electric circuit analogs, because the underlying differential equations are so similar. We can represent mechanical systems with equivalent electrical circuits. In the force voltage series analog, force is analogs to voltage, velocity is analogs to current, mass acts like inductor, damper acts like a resistor, and the spring acts like a capacitor. This is an incredibly powerful tool because it allows us to use mature circuit analysis and simulation software to study predict the behavior of complex mechanical systems. This our example, which is, say, draw a series analog for the mechanical systems of figure 2.17. Okay, this is mass mass S plus this is viscous plus K1 plus K2 over S L voltage 1 minus, which is viscous plus K over 2 fill V2 equal Fs. The second equation is minus viscous plus K2 over 2 over S, L voltages, plus Ms plus the summation of the viscous plus the summation of the springs over S multiplied by V2S equals 0. And this is our figure. So to wrap up, there are four key takeaways from this material. An undefined approach. We have seen that very different physical systems can be described by similar linear differential equations. A frequency domain using Laplace transforms simplifies complex differential equations into algebraic problems, making them much easier to solve. Impedance, the concept of impedance is the unifying trait that allows us to consistently model convenience across all of these different systems. Analogies, and finally, these mathematical similarities allow us to create analogies like modeling mechanical systems as an electrical circuits, giving us more tools for analysis. That concludes my summary. Thank you for your